for part 2 of quantum LDPC. Thank you.
So LDPC part 2. Okay, let me again start with a summary of what we seen yesterday. Yesterday we talked about constructions, and these constructions utilized so-called CSS codes, which are defined by two check matrices. Called HX and HZ. And the all-important condition was that HX times HZ transposed has to be 0. Okay. And as a first idea was kind of maybe we can kind of construct codes similarly as we construct them in the classical realm, which is just taking random parity check matrices. But then we very quickly saw that this condition essentially throws a wrench into this. So there's no naive random constructions. And maybe somebody remembers why that was?
Because if the one code has good distance, the other one can't.
Exactly, yes, because the checks of one code are code words of the other code. Yeah, yeah. So if this is a really good code, then this one can't have sparse checks. Yeah, but we want both matrices to be sparse in order to be LDPC. Yeah, so we need something more sophisticated.
Yes, is this proving a noble result for any CSS code, or is this just for this argument is only works for?
Oh, it's only if you want to kind of do this naive construction. Yeah, if you just kind of naively sample this to be a random sparse matrix, yeah, then it doesn't work. Then we kind of run into this trouble that we can't. That can also kind of randomly sample this one and be sparse.
I mean, I think isn't it true in general for the distance of the classical codes, but it's not true for the distance of the quantum code because you're modding out.
Oh yeah, of course, yeah.
Classical code, I think your statement's always true.
Exactly, yeah. So let me kind of drive that point home in a minute, because I saw like I had a few questions where people were confused about this. So let me just kind of say one more thing, and then I'll kind of give you again the geometric intuition. So what we've seen after this was that we can obtain CSS codes, so HX and HZ, by subdividing manifolds. And I use this word kind of very loosely. What I mean is just kind of subdivided into like vertices, edges, faces, and high-dimensional objects. Yeah, and then just look at the incidence relationship, and this incidence relationship gave me my parity check matrices. Oh yeah, and importantly, these manifolds had to be of dimension larger or equal than 2. Yeah. Okay, and yeah, so the kind of driving this point back home about which codes have high distance and which ones have low distance. So if we look at the code which is checked by HX, so this is called CZ. Then remember we have seen one example which was the Tori code, yeah, and we have seen that the elements in CZ were all configurations of loops on the square grid, yeah, and CXperp, which is the code that we mod out in the CSS construction, are all boundaries. Yeah, so just to kind of draw an example. So an element of CXperp would be something like this. Yeah. But there are loops which are not boundaries, namely this one, right? So we want the code which doesn't contain these non-trivial loops. Yeah. We want this one to have very low distance. Yeah, because this will be our checks, like some basis will give us our checks. Yeah. And we want the other, which also contains these like long, these non-trivial loops. these ones should be very long. Yeah. Okay. All right. Yeah. So we have seen the Tory code, which was a very nice, very simple construction, and it gave us a code with distance scaling as square root of n. Yeah. That's because the shortest non-trivial loop has length square root of n. And then there I kind of did this bit where I kind of explained in quotation marks the Breuckmann-Meyer-Lure construction, which was very, very complicated. And they obtained a distance fourth root of log n square root n. Okay, so this was Breuckmann-Meyer-Lure. And the important ingredient here was twisting of the manifold. Okay, but then I said maybe there's like another way of constructing codes, and this will be the main chunk of what I'm going to talk about today. And I already kind of talked about it a little bit yesterday, which was taking products. Actually, let me just kind of write down here. So alternatively, can construct by taking products. Classical codes. Okay, so let me reiterate this a little bit to remind you. So first of all, we've seen that, okay, the example I gave you was essentially this one, where we have two circles, and I argued that a circle I can identify with the repetition code, where the vertices are my checks, and the edges are my bits. Yeah, and then I can take a addition product. I obtain a torus. Yeah, and this was exactly the Tory code that we have seen before. Yeah? And I kind of claimed that if I kind of take more general products of two codes, C and D, then the incidence matrix between, let's say, edges and vertices that I kind of called del1 is given by the identity and then the incidence matrix of the code D, and then del1C, and then tensor parameters, and then the identity here. Okay, and the intuition here was that my I have two types of edges. The ones I call horizontal, and those which I call vertical. Yeah, they just come from different types of products, namely whether I take an edge here times a vertex here, so edge times vertex, or vertex times edge. Yeah. Okay, so let me just kind of go through this, give you like one example, one very explicit example. So this is not really a code, but just to kind of show you where this labeling comes from, because somebody asked about this yesterday, and I kind of appreciate that it's not really obvious. So let's call these two vertices A and B, yeah, and this edge I call V for vertical, and this one I call H, and these vertices I call 0 and 1. Then what's the thing I get out if I can take the Cartesian product?
Square.
Exactly, a square. And here my labeling is A, 0 of this vertex, which is the product between this vertex and this vertex, right? And then I have this vertex and this vertex. So here I have A1. Here I have B0, B1. And my edges are just vertical 0, vertical 1, yeah, which is just this edge times this vertex or this vertex, and then AH and DH. And then I can check that my del1 is just given. So first of all, like columns are labeled by the vertices, so sorry, by the edges, so AH, BH, and E0, 1. and the rows are labeled by the edges. So A0, A1, B0, B1. Okay, and then I have, let's say, I look at AH. Yeah, this is incident to A0 and A1. So I have 1, 1 here. And this is all that this edge is incident to. Similarly, 0, 0, 1, 1. And here I have 1, 0, 1, 0, and 0, 1, 0, 1. Yeah? You can convince yourself this is exactly, here I have the identity, right? As a product with the with del 1 here, which is 1, 1. And here I also have del 1, 1, 1. Yeah? So here I have the tensor product between the connector product between the identity and this 1, 1. And similarly, on the other side, I have the connector product between this 1, 1 and the identity matrix, right? Yeah, so it checks out. Okay, so that was just to kind of convince you that it works. Okay, and then the other thing I showed you was the Künneth theorem, which was quite nice because it relates the code words of these input codes of the factors to the code words that we care about in the quantum code. So, for example, I showed you if I have my code word on the repetition code here, 111, yeah, then this becomes this code word here, this non-contractibility. Okay, and this works more generally. So this was shown by Tillich and Seymour. Call this hypergraph product. And kind of plugging in good classical codes gives us parameters n, k of order n, and d of order square root n. Okay, so this again was just Künneth. And Künneth is not strong enough to kind of convince us that that this is actually the distance, right? It just kind of tells us there is a basis which has this weight, yeah. But there might be like some weird cancellations happening. For example, this is not a counterexample, but let's say I take this product and let me kind of just write the torus a little bit differently. Let me just kind of draw it in a planar way. Yeah, so the sides are identified here and here. What I could do is I can take an edge here. Yeah, this would pick up a syndrome. Yeah, right, because this parity check wouldn't be fulfilled, right? Here and here, but I can cancel it out by kind of adding an edge here. Right? So I can kind of cancel this non-trivial syndrome with a non-trivial syndrome here. Yeah? That's by adding an edge here and an edge here. Yeah? And I can kind of just go doing this until I kind of have created a loop. Yeah. But note that this actually has a larger distance than that's like one of the usual ones. Yeah. And essentially the proof is just kind of going through or kind of doing a proof by contradiction that if we have these kind of like mixed elements, then we can always kind of show that this will be lower bounded by any of the ones that we get from the Künneth theorem. Yeah. That's the high level view on this. Any questions at this point?
Sorry, I have a question. So what do you mean by the code word to be that loop? Like you said that like the blue line,
yeah,
is the code word for the quantum code. What's the quantum state?
Oh, we don't talk about quantum states here. Okay, so I really don't want to talk about this, but I mean, okay, just for you, like the state is actually the linear superposition over all elements in here. Yeah, and you can see that this is invariant under adding any like boundaries. Yeah. And the hidden information is like the non-trivial loop kind of hidden in this.
So that's just the standard CSS definition.
Yeah, it's just a standard CSS.
Just to make sure I understand the tumor result. So did this say that there exist good codes for which this lower bound on D holds?
Oh no, we can just take any. We can just take any.
Like asymptotically good.
Yeah. Yes,
results.
exactly.
So, okay, good. Okay, thank you. Please.
Is there a reason why you write the tensor products with the I on the left and I on the right? Because I would have thought they commuted. Or is there something you're implying?
Oh, yeah. So what I'm kind of implying here, and I kind of probably very likely won't go into this, is because these are products of vertices, right, and edges, right? So it only makes sense to kind of apply this on the edges. So that's why. And here it's the other way around. So here it's edges times vertices.
So is it a plus between the two, or
No, this is a tensor product.
no? I between I tensor round and
Sorry, where? Here?
yeah, that.
No, it's just a matrix. So this is just like kind of, I know, this is just like the block matrix.
Oh, okay.
Yeah, so like this. Yeah.
On the same note, the tensor product out there, do you think of it as a tensor product between graphs, or do you think of it more in the chain complexes?
Oh,
They're the same in this case, but I'm not sure.
so I mean, in this case, it's just like a coordinate product between matrices. So that's how I kind of set it up. But I mean,
Just in this idea that this loop, tensor loop is torus. That's
something again.
so the top diagram, you have loop, tensor, loop is torus.
Yeah.
So I can think of that as the tensor between the two graphs.
Oh, okay. Sorry. Yeah. So okay. So kind of again, I kind of didn't want to talk about this. So I actually it is a tensor product between chain complexes. Yeah. And what I'm kind of missing here is del2, right? I didn't write down del2, and I'm not going to. But yeah.
But in this case, it's also the tensor product between graphs, right?
Yes. Yeah. But I mean, so this is just like a linearization of this, right? And we can always kind of do this. This was kind of like what I was kind of alluding to during my talk, but not going to go into. But yeah, that's exactly what it is.
So another question. So here you're thinking more in terms of parity checks, but I guess you could define this also for the basis of generator matrix. But here we should think of these as defining parity checks.
Yes. So I'm not sure I understand the question correctly. So
I guess you could take like the transposes of these matrix and view these. I mean, the dual thing of the code it generates.
Yeah.
Rather than the check, but I guess you do here. You think of it as checks because you want the LDPC property.
Yes, exactly. So I mean, so here, so del1 will be. I mean, this will literally be the parity check matrix of the CSS code. Exactly. Yes. Yeah. Okay. Any more questions?
Sorry, I'm still a little bit confused about what the del operators actually are. So like del D, del C, are those like boundary operators?
They keep boundary operators. So yes, I mean, again, I want to kind of avoid homological algebra in this talk as much as I can. But I mean, you seem to be very eager. I mean, I'm also happy to kind of delve into that.
But I mean, just as a matrix, like, I mean, how should I understand this? Like, it acts on like vectors of edges. And
Yeah, it acts on vectors of edges and maps onto vectors of vertices.
Oh, okay.
Yeah. But the way I set it up was just like this an incidence matrix, which is also fine, right? It's the same thing.
Okay. And as an incidence matrix, it's given by the column vector 1, 1. Am I reading your notation correctly?
Yeah, right. So just kind of plugging in like this is just one edge, right? I kind of plug this in and I get like 1, 1 on the. I get the boundaries, which are just the two vertices here.
Okay.
Yeah. Okay. Yes, please.
Can you please write down the matrix, del1?
You mean here? Yeah, that's the matrix L1 for this.
Product matrix or one of the small ones?
No, this is the full. This is essentially like this one. Right? I just wrote down this one explicitly for this like little example. Okay. Yeah. Okay. Any more questions? Yes, please.
So in this case, if we commute C and D, we don't take the same thing. Or
Oh yeah. But I mean, this just happens to be because like I took the same code here, right? But I mean, if I made this one larger, I would kind of get like a maybe have like a thin torus, and otherwise I would like a thick torus, which is shorter. Yeah. Yeah. Yes, please.
so in the hypergraph product code, why are the qubits on these diagonal lines?
The cubes in the diagonal lines.
Hypergraph product code on the right side.
But this, I was giving an example of a non-trivial loop, yeah, which doesn't only consist of horizontal or only of vertical edges, but you can have like mixed. And then the thing I wanted to kind of get into was essentially for the distance, you have to kind of also take these into account, obviously, yeah, because Kunit only talks about like the ones which are kind of in one sector, yeah. And what you have to do is essentially kind of show that there's no way to kind of have like weird cancellations, such that the resulting loop becomes shorter. Yeah. And this cannot happen in this product. Okay. All right. Okay, very good. So everybody on board with hypergraph products. Okay, very good. Okay, so then let's move on to good LDPC codes. And we have already kind of seen the key ingredient in the Friedmann-Mayer-Luo example, and that is introducing twists. Yeah. So let me give you another example, and the example is of course the toric code. So let me. 1, 2, 3, 4, 5. Okay. So here, can everybody tell me the distance of this code?
6.
1, 2, 3, 4, 5. 5. Okay, so let me do something where I take this torus, yeah, and I twist it. Yeah? So now it looks like this. So, can we start again? Okay, and this and this, otherwise. This one. Okay, so what's the distance now? At least like for this loop. 10. So I go 1, 2, 3, 4, and I have to go back in here, right?
Yeah, 6, 9.
6. Yeah. So without introducing any extra qubits, yeah, so my n is the same, but I kind of just did this twist, and this introduces some detour that now my loop has to go, yeah, to kind of loop back onto itself to actually be a proper loop, yeah. And this is exactly what happened in this Friedmann-Mayer-Luo construction. I was kind of mentioning, yeah, where we kind of twisted some manifold, yeah, and kind of generated a code from that, and that gave us our extra fourth root of a log n. Yeah? And there were some rapid developments between 2020 and 2021, where essentially this type of idea was utilized. So let me just kind of summarize the results. So first, Evra, Kaufman, and Seymour gave an improvement over the Friedmann-Mayer-Luo result, where we now have an actual square root, not a fourth root of log n, square root of n. That was in April of 20. Then Kaufman and Tesla improved this further to arbitrary polylogs. So again, we have log n to the power s and square root n. That was in August. And then there was a bit of a breakthrough because actually many people kind of were willing to believe that this is possible. Yeah. But I think there were some people who had like an inkling that maybe this is the best we can do. Yeah, we can only have like poly variations of the square root n. But then Hastings and O'Donnell showed that this is actually not true. And they showed that it's possible to get distances up to n to the 3/5 over polylogs. Log n. And that was in September. And then Panteleev-Karachev further improved this and showed that actually you can get almost arbitrary, almost linear distance. 1 to alpha over 2, doesn't matter, 1 minus alpha over log n. And that was in December. Okay. All right, so we got almost there. The problem here was we had to kind of give up on the encoding rate. Yeah, so the encoding rate is also controlled by alpha, and it would just vanish if I send alpha to 1. Yeah? Okay. The idea here is essentially we take something which is a mix out of random and something which is structured. Yeah, so we take like twisted products of random classical codes. Yeah. Okay. So, any questions at this stage, or?
So these are still CSS codes?
Everything I talk about is CSS codes. Yeah, yeah.
So when you say twist, I mean, sometimes it's taken to mean that like, you know, the other side of the boundary is like literally Z2 flipped, and that's how you make the identifications. But here it seems like just somewhere in the middle of the lattice, you kind of shifted the coordinates by 1.
Yes, exactly. Yeah, that's the second interpretation is the one that I'm thinking of. Yeah.
And that's the one used in all of these results that you listed.
Yes, exactly. Yeah. So there's nothing happening on the level of how I do my parity checks at this stage. It's all about how it's all about like incidences and like how I choose my incidences. Okay. Yes, please.
Just keep on twisting. Just increase the distance.
But at some point, if, for example, if I do it here, then at some point I can kind of have a shortcut, right? If I kind of twist more than 180 degrees, I don't actually gain anything. Yeah.
In this example, though, if you twisted one more, if you went down by 2, would you get
Yeah.
7?
Yes.
So it's
But
up,
the thing-
up to L on 2 or something like this.
Yeah. Yes. Yeah. But, square root L, I guess. But yeah. Because you don't want to. Yeah. Okay. Okay, and then another result was by myself and Jens Eberhard, and these were balance product codes. And that was also in December. And so we were kind of inspired by this paper by Hastings and O'Donnell, which, as I said, was randomized. And we kind of thought about, like, okay, what is kind of the geometric structure behind this? And the way we thought about this was through a product called balance product, which is kind of like a widely known and used notion in homological algebra and topology. So let me just kind of introduce this real quick. So the idea is we have some group, G, acting on a topological space. Let's call this X. Yeah. So for example, we can have G to be a cyclic group acting on X, which is just the loop graph, and it just acts by rotation, right? So it kind of maps some point X onto a point G times X, just by rotating around. By rotation. Now let's say we have one group acting on two spaces, x and x prime, then there's a natural action of G on the product. Namely, if I have 2 points, x and y, yeah, then I can define the product to be x times G inverse, and then G times x, yeah? Sorry, y. Okay. And maybe intuitively you can already kind of see that this kind of final does some kind of weird twisting in the manifold. Now the balance product is simply defined as follows. So we take, so first of all, it's notated as x and then Cartesian product with a G. And then this is defined as just the normal Cartesian product. And then I just look at orbits under this action of G. Okay, so that's just the abstract definition. Let me give you an example. And again, I use the torus. It's convenient. So yeah, okay. So let me first of all say, so the way we're going to use this, we have already kind of shown or kind of seen that we can think of classical codes vaguely as topological spaces. Yeah? We can associate them with a cell complex and look at the incidence relationship. Now the idea is essentially to take tenor graphs of two classical codes, yeah, which have this symmetry, which kind of share a symmetry, and apply this this notion of product. So let me use some colors for this. So let's say I have a repetition code of distance 6. So 1, 2, 3, 4, 5, 6. And another repetition code of distance 3. And on both of these, I can act by performing rotations of 120 degrees, right? I can rotate them by 3 turns, right? Both of them. So I have I can perform this product. And if I do this, first of all, I get a torus. No. But it's not the usual torus. But it's a torus which is kind of highly twisted. So kind of looks like this. Here. And then you have periodic bonding conditions. So this side is identified with this side, and vice versa. So let me draw it again, just as a with this rolled up. And it kind of looks like this. And then my vertices. And then this length 6 one kind of just goes around.
In the definition of the balance codes, balance product,
Yeah.
are you identifying orbits to a single point?
Yes, exactly. Yeah, exactly. That's what happens. Sorry, yeah, I went over this a bit fast, but yeah, that's exactly what happens. Yeah. Yeah, these orbits essentially kind of become orbits of checks. Yeah, and this defines the new code. So if I would kind of, so this is still identified, this side with this side. Yeah, I just made a drawing. So this is just like as good as I can do. Yeah. So imagine this is just like a torus, but now the squares are kind of like the lattice is kind of twisted. Yeah, it's not like the usual square lattice that you would kind of put on a torus, but it's kind of like a twisted one. And now, if you do your counting, so first of all, we know that on the torus, our number of encoded qubits is just a number of non-trivial loops. That's still 2, right? It's just the same topological space. It's just a torus, so it's like one going in this direction, the other going in this direction. You can also check that the distance is still 3. Yeah, just because we can have like this loop kind of going around, right? The red loop is of length 3. However, the number of edges is 12. Yeah. If you wanted to get a distance 3 normal tori code, we would take a 3 by 3 square lattice, right? And then we use John's formula, and we see that here n is actually equal to 18. Yeah. So we reduced the number of qubits that we need. Yeah. But we kept our k and our d invariant. Yeah? And that's kind of the high-level idea here, that by doing this kind of product, we still kind of can kind of somewhat preserve our code properties, yeah, but we reduce the number of qubits that we need. Yes, please.
I see you defined the action like with a right action on X and a left action on X prime. It's the same in the case of the abelian group that you use, but you use non-abelian.
Yeah, in the end, we have to use non-abelian groups. And that was essentially also like one thing which was different from like these previous works, where we just used where they just used like essentially abelian groups. But this actually allows you to kind of do non-abelian products. Yeah, I will get back to that in a minute. Okay. Like one additional thing is you can actually also prove a Quinlet formula. So just as for the hypergraph product, it's slightly more complicated in the sense that here we have a condition. So if the order of G is odd, then it follows that code words lived. Okay. And this is exactly what happens here, right? So we have our red loop lifts to this red loop, and our long blue loop kind of lifts to this blue loop, kind of going like in circles around the torus. Yeah. Okay. So now the main idea behind constructing good LDPC codes is, yes, please.
So it's clear n decreases because you're identifying edges.
Yeah.
Same orbit.
Yeah.
So why don't you lose anything in the dimension? Like the k would remain the same.
Oh, because of the Quinlet formula. Yeah, Quinlet guarantees you that as long as like G is not kind of co-prime with your field, in this case 2, you're good. Yeah. Okay, but again, it's not a guarantee. It gives you an upper bound on the distance, right? Because you might have created like weird shortcuts, which kind of give you like shorter loops. Yeah, but at least it gives you like some hope that if you take so the idea, take 2 symmetric good codes. Let's say on n tilde bits, and a symmetry group.
There's one more question.
Yeah, 1 second. So that the order of the group is of order n tilde. Yeah, so the question?
Well, I guess maybe if you were to say that like symmetric group means that the group of automorphisms contains G or something like that.
Yeah, so exactly. So that G kind of acts on the tenor graph. Is essentially what I mean.
Oh, okay. Yeah, okay. I'll let you guys chat.
Okay, so then the hope is that the output number of qubits n will first be n squared, n tilde squared, right? Which is just due to the normal product that we already knew, the hypergraph product. But then we reduce with respect to G, yeah. And if G acts regularly on the tenor graph, we reduce the number of qubits, and then here we will get n tilde. But kind of König kind of gives you at least the hope, so that the distance will be preserved. So we get n tilde, and this will be n. Okay. So we kind of hope that we can essentially reduce the space, yeah, but kind of preserve the loop or the code word which kind of lies within it. Yeah, that's kind of the idea. Is that kind of, did I convey this or? Yeah.
And here you don't really care about, you're happy with k equals 1 even.
Well, okay, actually k I know. K I know will be of order n, again because of König. Okay, so this brings us, okay, how do we even get these symmetric good codes? Oh geez, I'm completely running out of time. Yeah, okay, but that's okay.
You have another 15, 20 minutes?
Yeah, that's fine. So I can maybe do a little shortcut when I explain Zipf-Spielmann codes. So the question is, how do we get these ingredients first of all? So good symmetric classical codes. And these are defined from Cayley graphs. Where we take some G and generating set. Such that it's closed under inversion. And we define the graph just by kind of taking the vertex set to be the elements, the group elements. And two vertices are connected. Let's say like this, so G connected to G prime, if and only if there exists an S in S such that G prime is equal to G times S. Okay. And we can simply define a code, as we did before, based on the incidence relation between the vertices and edges. Yeah, so we just take the graph code, right? And we have already done this, right? So for example, G could again just be the cyclic group, Cn, and then we get our graph. Yeah, and this was just our repetition code, right? We could do this here, but it was observed by Zipf and Spielmann that we can actually get good classical codes out of this. So Zipf, Spielmann. And let me kind of shorten this a little bit. So let me just say, if the graph is sufficiently well connected, so what I mean is an expander, of course, and we perform local parity checks according to a length S code. Which has sufficient distance, yeah. Then the resulting code will be good. Yeah. So what do I mean by perform local parity checks according to some local code? So let's say I have one vertex in my Cayley graph, which looks like this. And usually I would just perform parity checks among all bits coming into this vertex. Yeah. But let's say, or maybe let's say 5, 6, 7. It makes more sense. But instead of doing that, I perform the parity checks of the 7, 4, 3 Hamming code. Yeah. So now I want to see a code word of the Hamming code around this vertex rather than a code word of the parity check code. Yeah. Is that kind of clear? Yeah. So for example, let's say, I don't know, this, and then I don't exactly know what the code words look like here, but let's say this is a code word of the Hamming code. Yeah, then this would be allowed. Yeah. But for example, this would not be allowed because the Hamming code has distance 3. Yeah. Okay. But now, because the graph is kind of expanding, or well connected, as I call it, if I want to generate a non-zero code word, yeah, I have to kind of put some non-zero elements somewhere. So let me kind of put them here. Yeah. Now I see that because this node kind of sees a single 1, yeah, I have to kind of make up for it by kind of adding more ones, let's say here and here, yeah. But these expander graphs, they look locally like trees, yeah. So whenever I kind of try to fix something, I just kind of create more problems for myself. Yeah, I have to kind of put more ones, yeah, and so on and so on, yeah. And I hope I can kind of, I know, gives you the intuition that in order to kind of fulfill all checks, I actually have to kind of put ones on order n edges, yeah. Assuming that the graph is like well enough expanding, and this local code has like large enough distance. Yeah. If you have not seen this before, then I would kind of urge you to kind of check out Zitzler-Spielmann's paper, because it's a very, very simple, very elegant, very nice proof of this. Let me also mention, just because I like the notation very much, and if you're an homology aficionado, then you might like this. So Meshulam showed that this is exactly something that we kind of already know in homology. This is called homology with local coefficients. Okay, and this is traditionally denoted XL, where this is my graph, and this is my local code. Okay. So these are the ingredients. Any questions while I erase the board? Yes, please.
So there you said that if the graph, presumably the Cayley graph, is sufficiently well connected, and the way you define the Cayley graph, it depends on the generating set. Like, I mean, I guess this is probably a basic algebra question or something, but can you imagine a situation where you have the same group, but you take like a different generating basis, such that now the Cayley graph is somehow, like, I mean, with two different choices, with one choice you get the other one you don't.
Yeah, indeed, it does depend. It does depend on the generating set. And actually, let me kind of give you the example. So, okay, let me say two things. So first of all, we know that like one way of kind of getting a symmetric well expanding Cayley graph, actually optimally expanding, is and this is a result due to Wygotsky, Phillips, and Zanak, and also Meshulam, that if you take G to be PSL2 FQ, then there exists a distinguished generating set, yeah, such that it's optimally expanding. It turns out that if we take any finite simple group and we take a random generating set of sufficient size, this will also be an optimal expander. Yeah. Okay. Now, kind of knowing this, and kind of knowing that we can take random local codes, yeah, they will have large distance. This led Jens and myself to conjecture. Yeah, that balance products over G lead to good LDPC codes. Yeah, and this was spectacularly proven by Panteleev and Kalachev. So they gave an ingenious proof. Panteleev, Kalachev. In 21. And essentially what they showed is they use a higher dimensional version of the Zipf/Biermann proof. Yeah, but in contrary to the Zipf/Biermann proof, which is like very short and sweet, yeah, it's really a tour de force. It's like really complicated to kind of make your way through this higher dimensional object. So let me just kind of, because I kind of introduced this notation earlier, let me just kind of write down what it looks like. So we have C, and then we have our calligraph X, and then local code L, and then we have this linearized balance product. I didn't fully define this, but I just show you the notation. And then this we can actually identify with C, and then the balance product of the two calligraphs. And then we have this local system. Oh, sorry, this local code. So this is just a balance product of TSL to Cayley expanders. Yeah. In the paper by Dino and others, they call the C-cubed LTC paper, they call this left-right Cayley complex. Yeah, where this essentially kind of comes from the fact that we have our group kind of acting from the left and the right, yeah, on our graph. Yeah, and this is a tensor code. Yeah, and the technical ingredient that Panteleev and Kalachev found in order to kind of show that, okay, so maybe I should say, essentially we would want to mimic the proof of Levry and, of Telic and Seymour, where we want to show that these kind of cancellations that can happen in products don't happen. And the technical ingredient here was essentially kind of showing that, or kind of knowing that random like tensor codes made out of random codes have a certain robustness property. And I refer to Prahlad's talk, who will cover this.
It's just proving a good classical code, or like?
No, this is a good quantum code.
Sorry, does this like equality hold for any group G that you were plotting here, or is this specific to the?
No, this holds for any group G. There's like a difference between, so you can do different things. You can kind of dualize these codes, and then it doesn't work anymore. There's also something else you can do. So let me have also mention this. Wait, let me first write down. Let me first erase the board and then kind of write some things down.
I guess, Nikolas, this itself is an identity. Probably it's not that hard. Then what you do with it is.
Yeah, of course. Yeah, sure. Yeah. I mean, in some sense, this is just a definition, right? I mean, this is already the mathematical object. This is just like a different way of describing it, right? I mean, this is just like saying, okay, I take this product and I get something. I could also just kind of first do the product here and then kind of plug on this like tensor code everywhere. And I know that it fits. Yeah, I just like it because it's kind of, I don't know, this associativity kind of looks kind of nice. All right.
Also, more than that, you really use the right-hand side to do the analysis, right? Because you use properties of the tensor.
Oh yeah. So yeah, that's kind of the important thing, because okay, let me kind of say one more technical thing. So I mean, I think what one could have tried is just take some. This is a high-dimensional expander, yeah, and just to kind of mimic the Zipf/Biermann construction. Naively, you would have just kind of taken a high-dimensional expander and just put like a local system on it, right? Which is exactly what Zipf/Biermann is in 1D. You just do it in high dimensions. Voila, you have a like high-dimensional object which has the same properties as Zipf/Biermann. you're done. I think the main ingredient is essentially kind of that you can kind of build high-dimensional expanders using a product construction. And this really helps you because you can always kind of use Kunet and all these kind of things. You kind of have more of a handle, right? If I would take like some weird Breuer-Titz building, yeah, then this becomes much more complicated. Yeah. Okay. 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 Okay, then let me just briefly sketch the argument. So first of all, I should also kind of say Levery-Seymour came up with a very nice construction. So what they did was just a different way of associating the tensor code, yeah, and that essentially led to a much more symmetric construction, yeah, which makes things much nicer to handle. Yeah, let me just give you a cartoon picture of the argument. So the idea is we just take the element W in CZ, which is smaller, such that W is, let's say, bounded by some delta times n. And then we show that there exists an element y in Cx perp, such that omega times y is strictly smaller than omega, w. Okay? And this is like the crucial step, right? Essentially kind of relies on the fact that if we take some loop, yeah, in this structure, yeah, then there's always some piece where we can kind of do some flips, yeah, but these flips will be boundaries, yeah, and this will reduce the length, yeah. But now we just kind of plug this back in, yeah, right, because we know it's still kind of smaller than delta n, right? We just kind of decrease it. So by iterating, we know that this will now be in Cx perp, yeah. Yeah, so it doesn't kind of go into the distance because we know that for CSS codes, so know that CSS code has distance because the distance, like only for z, so dz again into close definition, so was w in CZ, but then removed Cx perp. Okay. So let me just kind of say it once more. We take an element in CZ, yeah, which is small enough, yeah. Then expansion tells us we can actually kind of make it smaller, yeah, just by kind of adding elements in Cx perp, yeah, just adding these checks. This tells us that it has to be in Cx perp, yeah, but then it doesn't kind of go into the distance, right? Because this is going to take it out. Yeah, so this has to be really larger than this. Okay. Any questions regarding this? Okay. Since we are running over time, let me kind of just.
So regarding that argument is what Patley and Kolchev used, or is that where is this argument at first?
Oh yeah, this is Patley and Kolchev's argument. Yeah, exactly. Yes. But I mean, again, so the main really great thing that they do is essentially kind of show that the structure is essentially still expanding. Like it's still a boundary expander. Yeah, and then essentially kind of show that yeah, kind of this whole argument goes through. Yeah, which is highly non-trivial. Okay, let me just kind of now give like a couple more references, and then I will wrap up. So for similar arguments, by this I mean expansion, can be used for decoding. again, the idea was already present in Zipser-Spielmann's paper, where they kind of show that you can decode expander codes using a linear time decoder. Again, the idea is essentially that if we have some error, it will generate syndromes, and by kind of flipping bits, we can always kind of reduce the syndrome, and this gives us a greedy linear time decoder. And this was developed by Dinur for the quantum case, Shay, Lin, and Winnick, and also for the construction by Levry and Seymour, by Gu, Hutchison, and Tang, both in 23, actually like only a few days apart from one another. So it's a very hot topic. Okay, then another thing I should mention, so this is not only useful for quantum coding theory. I said like one other thing was you can use this to define C-cubed LTCs. The only difference is now you don't put your degrees of freedom, so you don't put qubits on edges, but you put bits on the faces. Yeah, this defines a C-cubed LTC. Yeah, so instead of taking the first homology group, you take the second homology group. Yeah, of the same object. And the third thing was it turns out that this distance proof can be generalized in a certain way, and this gives rise to a certain clustering property of things which are close to code words. And this then was very useful for proving a result in Hamiltonian complexity by Anurag Anshu and myself and Chimay Neke. And I think Chimay will talk about this in his talk. Okay, since I'm already over time, let me kind of stop here. Thank you very much.
Okay, maybe a quick question before we head off to lunch. Okay, these people are hungry, so thanks again, Nikolas, for allowing 2 talks, and we'll see you all.
Submit speed talk.